Welcome back to my Commodore 64 Memories videos. This is where I look at old Commodore 64 software and some of the technical details behind them. Today we have Wanted Monty Mole, released in 1984 by Gremlin Graphics, created by Anthony Grouther. Now this game is one of the earliest games that I can remember that had an auto-run tape turbo loader. There are probably earlier games than this which had an auto-run tape turbo loader, but this is the first one that I could remember. I also remembered that the version I had didn't let me reset the game properly. So let's get into it and have a little bit of a deeper look in ICU C64. Pay close attention to this area in memory because this is where the tape header memory is, and there we go, it's filled with what looks like code and data even before the file name is displayed on the screen. And then of course it goes into this tape turbo loader, which is loading relatively quickly, but that's because I'm warping through it in the emulator. Let's open up the sprites view, and yep, we can start to see, even when the game hasn't finished loading, we can start to see some sprites in the very first Vic Bank there, in the latter half of the first Vic Bank. So in the memory range between 0 and 4000 in hex. Also, we can see there some character set information at the beginning of the Vic Bank, or near the beginning of the Vic Bank, probably the first character set, starting at 800 in hex. There seems to be some structured data later on in memory, and there also seems to be some code or other data in the middle of the first Vic Bank, which doesn't seem to translate into sprites or character sets. So once the game finishes loading, look, it renders a quick little maze in the top half of the screen, or top quarter of the screen, and then we get into this title screen with some music going on in the background, and we have a little Monty Mole sprite dragging across a Monty Mole sprite-based banner across the screen. We can see that the screen is actually using the default screen area, which is 400 in hex, which is the same as the screen area at power on. There don't seem to be any other character sets in memory apart from the character sets at, there we go, 800 in hex. It's multicolor, which is interesting. Monty Mole, the second game, right? I think it used high res or extended color, not multicolored graphics, I don't think. But this one is using multicolor graphics. This is a very different game to the next Monty on the Run, right? Monty on the Run, I think, was published a year after this one. Let's get my debug views in their correct position. There we go. So we can see pretty much straight away that there's no dynamic sprites. We've got just the loaded sprites sitting there in the first bank in memory. It's a scroller. We seem to be having... we don't seem to be getting any color RAM updates, but we do seem to have that nice little green rectangle as an edge copy going on from the middle of the screen, middle of the memory there. So that's okay. So that's one of the... Is that the first or the second Vic Bank? I don't know. Might be the start of the second Vic Bank. We'll save a snapshot for use later on. See if we can maybe extract the map, perhaps. We'll do that later on. But yeah, it seems to be doing like an uncompressed map copy from somewhere just before the middle of memory. Now, if I have a look at the character sets in the ICU 6040 debugger, we can see quite clearly that the character set information is being animated. We have those several different animating sections there. what looks like the horizontal platforms opening and closing, and a vertical thing moving up and down. Okay. So let's move around the level, see if we can... Well, okay, so there's the horizontal left and right platforms. Look, there we go, straight away. So the characters for that are not being... The character screen characters are not being animated. It's actually updating the character set information. So the character set information, because it's changing, you don't need to see the characters, the actual characters in the screen are static. They're not moved at all. They're not animated at all. It's just the character set data. So the character set is used to display different characters, of course. And, oh, look, there's the moving up and down column as well. I think it's probably, like a fist or a door or something like that. There we go, just going to walk underneath it, and it's going to probably push me through or kill me, right? Let's see what it does. Ah, there we go, it pushes me through, and then I explode, and then the screen goes red, and then the RIP comes on the screen, and then that's it. That's the game. I never really got on with this early version of the game, to be honest. That's intriguing, though. Look, I could reset it, but it goes to a ready prompt, and you can do a list. Now, in the version of the game that I had, it didn't let me reset at all. It actually went back to the title screen. But let's have a look. Ah, okay, so there's an 80, an 80 there. Let's have a look at it in screen characters. Ah, there we go. Oh, yeah, so that's a CBM 80. So that CBM 80 at 8000 is basically a warm start vector. So when the Commodore 64 starts up, it looks for a cartridge ROM header at that particular memory address. Now, if you put the cartridge ROM header at that memory address, then it basically jumps to it during its normal startup routine and then starts executing code. Because the Commodore 64 doesn't clear memory when you do a reset, not by switching it off and on, but when you do a normal reset, then because the RAM is not cleared, it's just tested, which is non-destructive. It picks up this information and then it runs through the other startup routine. Which, if you have a ROM replacement cartridge which puts a ROM bank over the memory at 8000 in hex, then it will start up that cartridge. But because the data is in RAM, it's starting up the code, or it's running that code which is in RAM. There you go. If I ran the code again, then it just started the game again. But yeah, in the version of the game that I had, it looped back and went back to the title screen. Maybe I didn't quite have a particularly original version. So, okay, so there we go. That's intriguing. Look, that's the memory at 8000 in hex, and it's got what looks like assembly opcodes in memory. A little bit before as well, in the pages before 8000 in hex and the page after 8000 in hex. There's also some what looks like 53280, 53281. That looks like basic code there at 8400, 8400 in hex. So that's 33792, 84 in hex. In decimal is 132. Okay, so let's poke 44, 132, and then let's do a list. Oh, there we go. We've got the first, I think the second page of the basic memory, the second memory page of the basic coded memory that was left over has been corrupted by loaded data. But yeah, look, we have a fragment of a hidden basic program there up at 8400 in hex, or probably actually more accurately starting at 8401 in hex. If I'm guessing that the author put that code there because they knew that they were going to load in all of the game data. Anyway, let's have a look at the code, the code and data at 8408000 rather. That's code. That's code. 8100 immediately following. Wow, look at that. If I use the machine code monitor in Vice to run that code, we seem to get what looks like a monitor prompt. That's unusual. In this game, DE is usually disassemble, right? It's disassembled the memory location 0. I'm pressing the down arrow cursor key here, and it's disassembling in sequence the start of memory. And it's got an A command. Oh, A is usually probably, assemble, right? But, okay, X exits the monitor. So why is there a machine code monitor hidden in this game here? Maybe the machine code monitor is a leftover from a machine code monitor cartridge, because there's the cartridge ROM auto start header there. If I do D400 in hex, that's not D400 in hex, that's 400, that's 40,000 in decimal. Okay, so this looks like it's got decimal addresses. It doesn't look like it's using hex. It looks like it's using decimal notation for its addresses. So let's disassemble. Yeah, no, that's not going to work, is it? Let's disassemble 01024. Looks like it's got a 0 prefix there. Okay, so that's disassembled the space characters, right? And space character is 20 in hex, and 20 in hex JSR. Okay, so let's assemble some code at 1024, which is the start of that screen memory there. Let's use decimal notation rather than hex. Wow, yeah, look, that's A9FF at the beginning of memory. Look, there we go. Using the Vice monitor disassemble command, I can see the same thing. So yeah, it's a decimal based assembler and disassembler hidden in memory in this game. Well, that certainly probably explains why, when this version of the game, on this tape anyway, reset, it went into what looks like a ready prompt, because it's running some leftover vestigial code of a machine code monitor hanging around in memory. Wow, yeah, look, it's actually assembling code using the A command in the monitor. Wow. So that's really unusual. It's very, very unusual to find that kind of thing in a game. But, then again, this game is from a very early era in the Commodore 64 games. I think in a couple of my other videos, I did find small little leftover pieces of basic code, small little leftover pieces of like a PDS system, programmer development system or something like that. A ROM, a user port transfer routine, right? Which is what PDS used to use for transferring data into the Commodore 64. Certain versions of them anyway. I think other versions probably used like a direct write via the cartridge port, but I think some of them also did use the user port for transferring data quickly. So anyway, let's see if we can use 6510 Plus. So this, the monitor hidden in memory reminded me that in 6510 Plus, we also had like a machine code monitor or a disassemble command, right? We could use disassemble 49152, and it would translate that to C000, but you could also use hex notation as well. So let's see, instead of using the Vice monitor debugger, we'll just see if we can transfer this game, or at least try and reverse engineer this game with its auto run tape turbo loader, right? So when you want to try and inspect an auto run tape turbo loader without using freezer cartridges or anything else, just using a stock Commodore 64, you need to intercept the tape turbo loader the auto run part of it. And this code will do that. So what this code does is that it uses some of the kernel routines to open a file on tape, and it will then copy that data from the tape to up higher in memory, because the auto run tape turbo loader, like a disk auto run loading file, it usually overwrites the vectors way down at the bottom of memory, probably, you know, the stop key test vector or the character out vector or the get character vector, whatever. And that claimed vector will then be subverted into running the auto run code, right? So if we run that code, it will not allow the vectors to get overwritten. It will just copy it up into 16384. So it will copy it up into the next Vic bank rather than the first Vic bank. It will put it into the start of the second Vic bank, basically. And that will enable us to then save all of the data that we want to see, including all of the data in the tape header. There we go. The tape header gets filled first. It then displays the file name. Well, it had the file name in memory, but then I clear the tape header in the basic code, of course, because I want to see what extra data is loaded, if any. And it's copied the tape header and everything else into the second Vic bank, into the memory at 4400 or 4300 in hex, basically. So now it's waiting for me to press return. It's displayed the start and end of the extra memory that it would normally want to load, and 795 and 810 are in hex. 31B and 32A. Right, so 31B and 32A are definitely within the range of the vectors down in extended 0 page, right? So let's have a look at the ROM disassembly, see what we've got there. And yeah, it's loading data, or it's going to want to load data, but we're not going to let it. It's going to want to load that data over the beginning of the vectors. So that's why this tape auto run thing wants to start. And we've got the extra data there, but now we just use go to 200, which copies that final data that it wanted to try and load, but we stopped it from trying to load it there onto the vectors. We're just copying it now into the corresponding memory address, but plus 4000 in hex, which is plus 16384 in decimal. So now I'm going to save out that whole memory range of 4000 to 4400 in hex. We're just going to save that out to a file. I'm going to make sure that the true drive emulation is turned off and that the virtual device traps are on. So it just saves it as a file in which directory? Yeah, C:temp. Yeah, so it's going to save it into C:temp in the emulator, because I don't want the emulator to have to create a disk image and everything like that. I just want to save the file into C:temp on my PC. We will call it Monty Loader, because we want to just load that file later on, and it was the loader for Monty Mole, right? So we'll just call it that. We'll save it, (8), because we need to save it to the virtual device trapped drive, which will then save it as a file on the PC. Let's look at that file in the hex editor, and yeah, there we go. So we have data at 3189AB, right? And that was the data that was loaded over the vectors, and then the rest of the data that was in the tape header. So let's load 6510 Plus now, which is that old assembler, disassembler by Dave Weaver. And we'll load the Monty loader .prg file into memory, and we'll just disassemble it using 6510 Plus disassembler. So we'll start looking at 4300 in hex, because that's where we know that, there we go. Ooh, look, there's some code there already at 431B. Well, okay, so it loaded code over the beginning of the vectors, and then we have all of this extra code. It's a little bit difficult to look at it on a screen like this and to try and figure out exactly what it's doing. So what we can do is that we can print it out. So I don't have a printer, and well, I don't have a Commodore 64 compatible printer, let's put it like that. But what we do have in the emulator is that we have the ability to fake a printer and then print it out to a file system. So we'll output to a c:\temp.txt file there. And of course, if you want to print from a Commodore 64, you have to open 4.4 or any logical file number, and then cmd4 to output the redirect the output to that logical file number, which is 4, associated with the printer device, which is 4, and then issue the disassemble command. We can see the memory read going on. I think that's read the next page already, so let's break out of that, and then let's open the text file printer output. And there we go. So we're not interested at the very beginning because, well, data wasn't loaded up there. This is the start of the data that was loaded. Look, it's got some code. Load Y, JSR 351. This was tried to load. This was going to be loaded at 31B, right? But the basic code put that data up at 431B. It extracts it from the tape header, and then it pokes it into the right place in memory, right? 4,000 in hex. Anyway, so yeah, that next part after the code pointed to, right, this vector at 326, right? The vector at 326, which is mapped to the memory address 4326 by the basic tape loader peak code, right? It loads over that vector there. So yeah, that vector then points to code at 3F2, yeah, okay, which then does, yeah, okay, it's then jumping to 371, which is earlier in the code. Oh, that looks like a store of data, right, with a memory address increment. Okay, anyway, so 371, yeah, look, stop the interrupts, reset some of the vectors that were probably overwritten by the earlier code. Oh no, it's the vector before, actually. Okay, never mind. And then it's resetting the screen, or it's doing some stuff with the screen, setting up timers, okay, or setting up a timer interrupt. Non-maskable CIA2 interrupt, right? CIA2 timer, sorry. And then it's running, okay, so it's running some code here with timer set up and everything. Okay. Okay. No, it's reading the timer. It looks like it's reading the pulse length. Aha. Okay. Yep. So it's reading the pulse length and returning carry clear or carry set, depending on whether or not it's a long or a short pulse, I guess, from the tape. It looks like it's counting the number of certain lengths of pulses until the value in 9.2 stops, okay, yeah, until the value in 9.2 gets to 0, right? And then it looks like it's verifying that it's getting a different length pulse, okay? And then it looks like it's getting a byte by JSRing to 31B, right? 31B is actually at the start of that loaded vector. Really? Okay, yeah, okay. Okay, it's doing a load Y, JSR. Okay, yeah, looks like it's getting a full byte and then storing it to C3, C4, AE, and AF. Huh. Okay, this part of the code looks like it's comparing C3 and AF and C4 and AF and C3 and AE. Okay, high byte and low byte checks. If it's equal, looks like it's probably the end of the file that's loaded. Otherwise, if it's not, it gets a byte. Adds, stores, that's a checksum probably, and then a load Y, and then is storing directed with C3.Y. Okay, and then an inc C3, inc C4. So it looks like it's loading data, storing it indirected to C3.Y. Yeah, that's definitely an accumulated checksum. Gets the extra checksum. If it compares or not equal, it goes to FCE2, which is the reset. But it looks like, it's loading code and then jumping to it at 400 in hex. Okay, so let's try and get the second loaded piece of code that loads at 400 in hex. Right, okay, so what we need to do is that we need to alter that loaded code, right? So that instead of doing a jump to 400, we will jump to our own code, which saves the block of memory. And we can use the 6510 Plus assembler to actually assemble some code, which will save a block of memory to a disk file, okay? So let's reset 6510 Plus, clear the memory a bit, then let's get this code. So this code, well, let's have a look at the beginning of it first. So the beginning of the code resets the processor port so that it's back into default state. Oh, and it also stops interrupts, of course. It resets the vectors. It also resets I/O and everything else. It basically makes sure that the kernel is in a nice stable reset state, so that we're able to issue disk save commands and stuff, right? It then turns off basic, but it leaves kernel enabled, but it disables basic in case we want to save anything under basic, but we're not going to this time round. But I think when we load all of the game code, we're going to want to switch off basic. But yeah, it basically then checks for anything on the joystick being twiddled, say a fire button or something like that. So it pauses until you press the fire button. It then sets the start address at 400 in hex by storing it to 43 and 44 in decimal. Those are just zero-page memory locations which are normally used for the start and end of basic, right? It sets up the name, which in this case it's Monty Loader 2. It then sets the device, which is 8 for the disk, and then we're just setting the end of memory as well. So it saves 400 in hex to 500 in hex using FF, the normal kernel routine there. And then there we go, we assemble it, and then we just want to make sure that we're in C kernel temp again. And now we use the machine code monitor in 6510 Plus to save that piece of code, right? So we want to do the Monty, we'll call it Monty save loader 2 or L2 for loader 2. So we're saving the second. This is the code which hopefully will save the second loader in memory. The second loader being loaded at 400 in hex. And we know that it's not really loading much more than 256 bytes anyway, probably less. So we'll save out. Should we save it with that file name? Yeah, I think so. I think that file name's okay. And we'll just save it from C000 to C100. Just save it the whole page. We could save it up to C04E, but I just want to make sure that I save all of the code, right? That's just been assembled to memory. Right. So now what we need to do is that we need to get out of 6510 Plus, and we need to load, first of all, load the Monty save L2 code way up into the high part of memory at C000. So we're going to get back to loading that tape auto run peak code, right, which stops the auto run from working and transfers the code or the data, code and data basically, up into the higher part of memory. So we'll load that again, and then once that's done its thing, once it's put the code and data up into 4000 in hex, well, 4300 in hex really, now what we need to do is that we need to patch that loaded code and then transfer it back into the right place in memory and then call it and then start it, right? Because we need to load the second loader. And we can only really load the second loader by calling the code in the first loader that was loaded. But that first loader is going to get patched so that it runs the saving code. I need to load that saving code that we assembled just now, right? I mean, yeah, I mean, this code is fine. That basic code there is fine, which transfers it from 4,000 in hex down to the first page in memory. But yeah, I need to load that loader code. I forgot that. So yes, let's load. What did I call it? Monty. Gosh, can't try to remember now. Yeah, Monty. Yes, current directory is fine. Yeah, Monty save L2 for loader 2, right? And 8,1. We should see it load, relatively high up in memory at 49152 in decimal. There we go, C000 in hex. Now knew that, otherwise basic pointers get a bit confused. And now we can enter that code by pressing return on each line again. And now when I run it, fingers crossed, when I run it, it will copy the patched version of the turbo loader back into the beginning of memory and then run it. There we go. We can see that it's loaded the second turbo loader now, and it's just waiting for me to press fire. This is the save code which was assembled with 6510 plus. And there we go. I pressed fire and it's saved the data file. Let's have a look at that second saved data file. There we go. Starting at 400 in hex, and we've definitely got some code, extra loaded code there. So now we need to inspect that code with 6510 plus. So let's load the second loader now into memory. Oops, I didn't type in open quotes. There we go. Let's load that. Now we cannot disassemble this directly because when we disassemble, we're going to make the screen data scroll off the top of the screen. So we'll use the monitor command to transfer 400 to 500 in hex to 4400 in hex, right? The second VIC bank. Now we can disassemble 4400 in hex, and we just need to remember that it should be at 400 in hex when we're having a look at the disassembly. So we've got a good disassembly there, but like last time, we need to create a printer output file. So yeah, we'll redirect the output to the printer. We'll issue the disassembly command again. And then hopefully what we get is that we get a good disassembly. I can see the disassembly already zooming off through the memory read there in the ICU 64 debugger. And yeah, this is the disassembly. So yeah, look, it's restoring some of the vectors, default vectors from FD37. That's intriguing. And it's storing it at the 31B. That's really intriguing. Okay. So yeah, FD3. Yeah, look, it's vectors for OS. So yes, it's copying those from the kernel and it's putting them back into the normal vector table. It's then copying a whole bunch of more data from 45D and then storing it at 2A7 onwards. Okay, so it's copying code or data or both. It's then doing some checks. Load Y44C300. Okay, so it's just copying some sparse data around or something like that. Is it? Maybe, possibly. But yeah, this is the important thing. Look, it's doing a JSR to 3F2, which loads the data, and then the jump at 449 in hex looks like it's starting code there. So we need to patch in. Well, we need to patch the second loader. And before it's called by the first loader, we need to tell that to run a real save routine now. So our real save routine, we can assemble that up already now in 6510 plus, right? Our real save routine now is going to save out a whole chunk of memory from the beginning of memory at 801. Yeah, we want to code now to save out the whole of memory, right? So yeah. We'll write that code in 6510 plus. and we want that code to run after the second loader. Yep. But we need to patch. So we need to patch the first loader to then patch the second loader to then call the final save routine. Right? Yes, that's what we need to do. So because we've stopped the tape auto run from working, right? We can do all of this now. We just need to remember the sequence of things that we need to do to cause this double patching event to happen so that we can call the final save code. So yeah, the final save code is going to look like this. It's pretty similar, almost exactly the same, apart from it's saving a different memory range. So it's going to start from 801 in hex here. It's going to use a different name, Monty, rather than the saved out second loader Monty code, and it's going to save out all of the data all the way up to C000. We assemble that, and we're going to use the machine code monitor again to save out that code, just making sure that the virtual device traps are still enabled. So we'll call it Monty save this time. And we'll put it at C000, which is 49152 in decimal, like last time. So this time, I'm just going to drop the Monty save code on there, first of all. So now that's loaded. The Monty save code has now been loaded into C000 in memory. I need to use the new command to avoid the basic start and end addresses being a bit confused. We'll then load the auto run tape peak code again, and now we're going to get it to load but not auto run the first loader like before, and we'll make sure that the rest of the loader code is put up into the memory at 4300, into the second VIC bank basically. Now we knew that, because now what we need to do is that we need to issue some patching of the patching pokes for the first loader. So we'll patch the first loader to run code at 193 times 256, which is C100 in hex, right? But yeah, 193 times 256 is going to patch the first loader, right? So this is patching the first loader, but at 4300 in hex, right? But yeah, we need to just getting my thoughts straight, right? We need to alter this loader to alter the second loader to then call our final save routine at C000, right? Yeah, that's what we need to do. So yeah, we need to have like a little micro patch now. We could have put that in the assembled code, right? But instead of going back into 6.0 plus, we'll just hand assemble it, right? So 49408, right? 49408 is C100 in hex, which is 193 times 256. So yes, we want we want load accumulator and then store accumulator and then jump, right? Which is going to be this. So A9 is 169 in decimal. Load accumulator is A9, of course, and then we want A9 192. Yep. Then we've got 8D, which is 141 in decimal, and then we store that at 4 times 256 plus 75 in decimal, which is that first loader address, which then tries to jump to the second loader. We're altering it to make it jump to our patch code, which will then so we're telling the first loader to run this second code, and this second code patches the second loader to then run the save code at 49152 or C000, right? And that 76 is 4C, which is the jump instruction, which then jumps to 400 in hex. Yes, that's what we're doing. Just making sure that all my pokes are correct. I think they are, right? Load accumulator 162, store accumulator there, which is storing the value of 192 into the loaded second loader. Yes, instead of calling the game start, it's going to call our save routine. Yes, okay, good. Right, my brain hurts. So now what we need to do is that we need to transfer the patched first loader into the right place in memory and then sys1010 to start it. Okay, so that's what that code does. And now it will run the code to load the second loader, which has now been patched. Already it's been patched. And then at the end of the tape turbo load, it's going to call our save data routine. Fingers crossed. Everyone cross their fingers and cross their toes and cross everything. There we go. The screen has been enabled. The border is flashing, indicating that we're waiting for the fire button to be pressed. I'm just going to open the directory, which is where the emulator is going to save the file. Right. So if I press fire, make sure virtual device traps are on, true drive emulation is turned off. The correct directory, working directory, is there, C colon temp. Yes. The emulator is doing a read, green read of the memory, and then saving out to a file. Fantastic. And then the emulator is just doing that ink border color thing at the end. So let's just load that file, right? So let's load the file. There we go. That's this whole game file now, I think, saved from 801 in hex. We've got the sys at the start. We've got blank area of memory at the end. But yeah, we've got all of the data underneath the basic ROM, right? Because basic is at A000, 8000 in hex, right? All the way up to BFFF. That's where the ROM is for basic. So we need to switch out the basic ROM to save the data underneath it. There we go. We load the file, run it, and hey presto, there we go. That is the game. Basically hacked using old school tools. Now if we take, we can play the game as well, so it seems to be working fine. If I reset it, there we go. I reset it and then it goes back to the title screen again. So, maybe I didn't have a completely original version of the game. Not a surprise, I suppose, because, oh, look, the second reset doesn't go back to the title screen. Now, that's interesting. So the first reset went back to the title screen, but this second reset is not. Anyway, so let's use my modern compression tool to compress that extracted file and then compress it with the start address of 33682, right? And we'll see if that works. It should do, right? Because, yeah, there we go. Look, the compressed file is a lot smaller, of course, because it's using modern compression. And yeah, the game loads and runs fine. No problem at all. Fantastic. And now if I reset it, and a second reset. Oh, second reset now goes into, I guess. Okay, so I guess that the reset vector is probably hitting some partially weirdly initialized data in memory. And then depending on the state of that memory, yeah, it's either resetting and going back to the title screen or not. Anyway, so there we go. Hacked and packed version of this game using mostly old tools and methods. So yes, let's load that previously saved snapshot into Charpad. The character set was at 800 in hex. The width and the height would assume that it's 256. Oh, there we go. That was really easy, wasn't it? Yes, the width of the map is 256 bytes, and then the height is probably around about 64 bytes. Characters. We'll change it to be multicolor mode. There we go. And then we'll scroll around for a bit, see what we can find in the map. So it's not quite 64 characters high. Oh, well, there's one message in memory. Hello, my name is Tony, telling you to be aware of above. Keep out. Okay, and then there's another one. Mind your head, there is danger here. Ho, ho, ho. Do not fall too far. Gremlin Graphics. Look, there's a Gremlin Graphics logo in the middle there, which you can play through. I've never really seen this because I've never really played through the game. Okay, the sky at night, acid bath, Arthur's castle, and then the end all the way on the right hand side there. If we scroll along now to the left, along the top of the... there we go. Okay, so that's the top of the map. So yes, if you like these kind of technical deep dive videos, then please do consider liking or subscribing to this channel, or sending me a super thanks. They are always very much appreciated. Take care, have a great day, evening or night, wherever you are.